We are discussing valence bond theory for dihydrogen molecule. We have proposed some kind of a wave function and we now seek to find the energies, and what these mean will become clear by the time we are done with the discussion of today. This is what we know already. We know that we have written the Hamiltonian for dihydrogen molecule, and using this approximation, Born-Oppenheimer approximation, we have ignored the kinetic energy terms of the nuclei, and we have also said that for a given calculation we can take a constant value for capital R. The problem is that this R12 is definitely not a constant. That is why we have to try to find a roundabout way of ascertaining the energies of this simple dihydrogen molecule. And this is where we had reached. We had reached this Heitler and London wave function, where Heitler and London took a linear combination of psi 1 and psi 2. Psi 1 essentially says electron number 1 is in 1s orbital of atom A, electron number 2 is in 1s orbital of atom B, and psi 2 describes the opposite situation, where electron number 2 is in 1s orbital of atom A, electron number 1 is in 1s orbital of atom B. And this is the Heitler and London wave function when the internuclear separation is something that we want to talk about, not necessarily always equilibrium bond length, but close by, where we do have interaction between the two atoms. So, this is where we got so far. We have not written out the Hamiltonian, and we are actually not going to write out the Hamiltonian at all in this course, but this is what it is. We have written out the wave function. Now, I do not know how to solve this equation. How do I go about it? The way to go about things like this, once again, was actually well known. So, this is a very standard method. This might look new to us because we are doing it for the first time, but these are very standard methods of tackling problems like this. So, what we do is we left multiply by psi 1 and then we integrate over all space. Now, what space is, what are the coordinates, all these questions might arise. Please hold on a moment, we are going to come to it and you will see how things simplify. We will show you at least one part and then we are going to take the rest axiomatically. So, left multiply by psi 1 and integrate. What do I get? I get something like this. Psi 1 H operating on psi 1, I can take C1 out and then I integrate this. I will just write d tau for now plus integral, well C2 I should write psi 1 H operating on psi 2. For now I will just write d tau is equal to E multiplied by C1 integral psi 1 d tau. Remember 1s orbitals are real, so I am not writing psi 1 star at all. None of these quantities are real, are imaginary, plus C2 integral psi 1 psi 2 d tau. And I hope we are by now sufficiently conversant with this bracket notation, so that we will not write these integral signs anymore, we will just write this C1 integral psi 1, well as you know this actually means psi 1 star, but here psi 1 and psi 1 star are same, integral psi 1 h psi 1 d tau plus C2 integral psi 1 h psi 2 d tau is equal to E multiplied by C1 integral psi 1 d tau plus C2 integral psi 1 psi 2 d tau. Okay. Remember what psi 1 and psi 2 are. They are really products of these 1s orbitals and also 1s orbitals occupied by electron number 1 or electron number 2. So, this will require a little bit of working out, it may not be as simple as what we might think just by looking at it. So, we will go step by step. First let us worry about integral psi 1 d tau. Well, just looking at it you might think that it is equal to 1, but hold on a little bit, let us see whether it is actually equal to 1 or not. Let us see. First thing to realize is that this is really a double integral. Integral in terms of coordinates of electron number 1 and coordinates of electron number 2. So, this is what it is, and a double integral, as we know by now, can be written as a product of two integrals. What are the coordinates here? Coordinates of electron number 1, coordinates of electron number 2. So, this we can separate and write as a product of an integral in electron number 1 and an integral in functions in coordinates of electron number 2, like this. Integral psi a1 integral psi b2. First one in terms of coordinates of electron 1, second one in terms of coordinates of electron 2. Now we can rest easy. We know very well that this psi a and psi b, these are essentially 1s orbitals which are normalized already. So, each of these integrals is equal to 1, 1 into 1 is 1. So, first integral is already worked out and it is equal to 1, that is a great relief. Now let us talk about the second one. What is integral psi 1 psi 2, and here we might be inclined to say right away without thinking much that it is equal to 0, it is not 0. Okay? We will see what it is. Remember, we are talking about different electrons, different coordinate systems. Let us expand. Integral psi 1 psi 2, that will be equal to replace the expressions for psi 1 and psi 2 here. This is what you get, integral psi a1 psi b2 psi a2 psi b1. Again what we will do is we will write this as a product of two different integrals, one in terms of electron number 1, the second in terms of electron number 2, like this. Now what do we have? Integral, so psi a is essentially 1s of atom A, right, and electron number 1 is what determines the coordinates there. Integral psi a1 and integral psi b1. What is psi b? Psi b is your 1s orbital of atom B. Now when you multiply these together and integrate, do you get 0? Actually you do not. Why not? Because these are different atoms, right. So I have written that it is S square and S is overlap integral. What is the meaning of overlap integral? That is something that we are going to see. So basically integral of 1s A and 1s B, that is what we are trying to look at. To do that, let us remind ourselves of these contour diagrams that we are so familiar with. Let us say the first one here is for A, second one here is for B, and remember the outermost contours tend to 0. The point at the middle, that is the maximum plus or minus value, and then they gradually taper to 0 as you go out. Now this situation here, let us say, is something like this, where they are at infinite distance apart, no interaction at all. What will be the value of this S, integral psi a psi b? What will be that value? It will be practically 0, because in order to get that one, what do I have to do? For at any given point I have to multiply the value of psi a by the value of psi b, and then I have to add up this product for all the points. Now if you think of this point, for example, we have some finite value of psi a. What about psi b? Psi b has decayed to 0 here, right. So there is no point where both of them have non-zero values. So it is practically 0 when they are far apart. What happens when they move closer? Now see, in this area where the two wave functions have overlapped, so to speak, now at this point, for example, there is some value of psi a, there is some value of psi b also. Multiply them together, you get a non-zero finite value, and then you just add them up for all the values, that will be some value that will be proportional to this area of overlap. Okay. Let me show you an illustration that Professor Arindam Chaudhary, my colleague, has worked out very nicely. So this is a depiction of two 1s orbitals at some separation. Now see, the area under this curve is very small. I mean the common area under the two curves is very small. So if I want to calculate the overlap integral, what do you have to do? Multiply this by this value, multiply this by this value, add up. When you do that, this is what you get, a rather small value here. and you see it is 0, then it rises quickly to some non-zero value here and remains constant and then falls off. What happens when the orbitals move closer, when r is smaller? Now there is a bigger overlap. So, this is the calculated value of the overlap integral as well. So, what has happened? We will go back once. Now look at this. What do we have here? We have sort of a tabletop, right, a plateau. That plateau has become narrower, that is point number 1. And the second thing is that of course this area is going to be much more now. And as you keep bringing the 2 nuclei closer and closer and closer, this overlap integral keeps increasing. Okay? You can also say that it becomes a little sharper, but what is more important is that it keeps increasing, and the limiting case would be when r if would be equal to 0, then the 2 wave functions would overlap completely and that integral would have a very large value, something that is depicted by this increasing overlap integral. I will just, for the dramatic effect, I will show you once again. This is what it is very far away. As they come closer together, you see this keeps increasing. And the same thing would happen if you take a minus combination. It is just that the product would be negative, nothing else. More about that when we come to it. Now let us get back to what we were showing you. Yeah. Now see, this variation that you see there would sort of look like this. 0 at capital R equal to infinity, then it would increase and then it would saturate to some value. Okay. This there is a problem in Macquarie's book. I have no idea why I wrote the expression twice, sorry about that, it makes it a little ugly. But there is an expression in Macquarie's book, there is a problem in Macquarie's book where this kind of an expression can be worked out for the dependence of the overlap integral S on the internuclear separation capital R. Okay. So, that is what it is. First thing we learn is that overlap integral is very much capital R dependent. Let us remember this will have a profound implication in our discussion of energy of this dihydrogen molecule. Okay. Knowing that, we will proceed a little bit. We know already that this is S square, we know what S is, great. What is the next step? Do we know what this integral is on the left hand side? Integral psi 1 h psi 1, actually we do not. Remember psi 1 here is a 1s orbital. So, it is an eigenfunction of the Hamiltonian for a hydrogen atom. The Hamiltonian that you see here is not a 1 electron Hamiltonian. It is the Hamiltonian for a dihydrogen molecule, which we saw has many more terms than a hydrogen atom. So, psi 1 is not really an eigenfunction of Hamiltonian here, otherwise things would have been very simple. We do not know what this integral is, we do not know what to do with it. At this point what we do is we just give it a name, we call it H11. Why H11? Because you have H in the middle, on the left hand side you have psi 1, on the right hand side you have psi 1, 1 1. So, this is called H11. Might sound a little funny, but actually very useful notation. What will the second one be then? If this is H11 integral psi 1 h psi 1, second one what should it be? Integral psi 1 h psi 2, it should be H12 by the same logic, yeah, that is what it is. And then the next step is to work out expressions of this these two integrals in terms of something else. We are not going to go through all that math in this course. If you are interested, I have this NPTEL course, another NPTEL course on quantum chemistry of atoms and molecules. There it has actually been worked out, or you can read standard quantum chemistry books by Levine or Pillar or Macquarie or whichever book you are comfortable with, Prasad, anything, and there it is worked out. So, without going into all that mathematics, without going through all the steps, let me just tell you that it is written in terms of some integrals that we are going to talk about later. What do I do with the right hand side? Well, once again, as I said, this mathematical manipulation is something that was sort of known for systems like this. So, it was known that it becomes simpler if I take everything on the right hand side to the left hand side, so that the right hand side becomes 0. then it becomes very comfortable. So, this is where we are right now. We have defined these integrals as Hii and Hij. Well, so far we have only talked about H11 and H12, but H22 and H21 will also come very soon. And this is an equation we have here, C1 multiplied by H11 minus E plus C2 multiplied by H12 minus Es square equal to 0. Now, what are the unknowns here, C1 and C2? Of course, you might say that H11, H12 everything is unknown, what are you talking about? No, but well, let us for now assume that we have some way of figuring out what H11 and H12 are. C1 and C2 are the unknowns. Now, two unknowns, I need another equation. How do I get the second equation? Simple, start from here once again, H operating on C1 psi 1 plus C2 psi 2 equal to E multiplied by C1 psi 1 plus C2 psi 2. In order to get to this equation, we had left multiplied by psi 1 and integrated. Now, just left multiply by psi 2 and integrate, we will get another equation, and I encourage you to work it out yourself exactly similar way as what we have done so far, and this is what you get. C1 multiplied by H12 minus Es square plus C2 multiplied by H22 minus E equal to 0. And one thing I want to say is that here it should have actually been H22, but because of a particular property of Hermitian operators, there is something called turnover rule, it is okay to write H12 instead of H21, no problem. Hij is equal to Hji, okay. For now just believe me on that. Now, this is the system of linear equations that we have. I hope we are all comfortable with writing this in terms of a matrix equation. Now, see, we have an interesting situation here. Right hand side is a null matrix. How do I get what are the possible solutions of this equation? Well, one solution is C1 equal to 0 and C2 equal to 0. And if C1 equal to 0 and C2 equal to 0, then we do not have to care about Heitler and London, we can just go home. We are not interested in that solution. So, we are interested in non-zero solutions of C1 and C2. When are we going to get non-zero solution of C1 and C2? Well, we are going to get non-zero solutions of C1 and C2 if the inverse of this square matrix cannot be worked out. Why? Because this matrix is A. Let us call this A. This matrix I will just call C. This is null matrix 0. So, suppose there is an inverse of A. A inverse multiplied by A multiplied by C is equal to A inverse multiplied by 0. So, if inverse exists, then once again we are left with this trivial solution of C1 and C2 both being equal to 0. That is not such a happy situation. So, the only way, the only saving grace that can be there is if the inverse does not exist. When does the inverse of a matrix exist? When the secular determinant, this determinant is non-zero. Now, we are in this strange situation where inverse should not exist for us. If the inverse exists, then we will get C1 and C2 both equal to 0. So, we can only have a hope of getting non-zero C1 C2 values if the secular determinant is equal to 0, that is inverse of this matrix does not exist. So, this is your secular equation, secular determinant equal to 0. Now, see, if I expand this, what will you get? You will get a quadratic equation in E, and therefore, when we solve it, in principle it is not very difficult to understand that we will get two values of E, two roots, and these expressions for E will be in terms of H11, H12, H22 and S. So, we have made some advance. If we somehow can simplify the expressions of H11, H12, H22, then we know how to get an expression for E. And now we are going to skip that part. As I said, this is discussed in detail in my NPTEL lecture of quantum chemistry of atoms and molecules, and it is there in all standard quantum chemistry books. Just believe me when I say that H11 turns out to be minus 1 plus j, where j is a Coulomb integral. What is Coulomb integral? Let us wait until we discuss molecular orbital theory when we discuss Coulomb integral in a little more detail. Good thing about molecular orbital theory is that during formulation there is no electron number 1, electron number 2, it is easier to understand. and this -1 is in atomic unit. So, this is really the energy of hydrogen atom. So, whatever energy we write later on is with respect to 2 isolated hydrogen atoms, okay. 13.6 electron volt, remember, that is the energy of one hydrogen atom. So, this is what it is, H11 and H22, it can be shown, will not be shown here, is equal to -1 plus J when everything is in atomic units. When we plot this, once again this is a problem worked out in McQuarrie and Simon's book. It turns out that even J can be written like this, e to the power -2r multiplied by a polynomial, and now J turns out to be a function that goes through a minimum. Profound importance when we talk about the energy, alright. But we have figured out HII, what about HIJ? Again, please believe me for now when I say that Hij turns out to be minus S square plus k. Now S we know, what is k? K is something called exchange integral, an intriguing quantity for which there is no classical analog. It is an absolutely quantum mechanical phenomenon. Once again, please bear with me for a few lectures until we get to molecular orbital theory. There we are going to talk about exchange integral in much more detail. Great. Now the variation of k with capital R is also qualitatively similar to this. It goes through a minimum. The difference is that it goes through a much deeper minimum. Now again, without deriving it, but this part is not very difficult. If you just plug in these values of -1 plus j and for H11 and H22 and minus S square plus k for H12 into this determinant, you can work out yourself that the two roots that you get will be j plus minus k by 1 plus minus S square. I have cheated a little bit because I have eliminated another term that would be there. That term would be the energy of 2 isolated atoms, and remember right now everything is in atomic unit. Okay. So, this is really energy relative to the energy of 2 isolated atoms. This is what you get, right. So, these are the energies. What about the wave functions? We will stop here and we will come back and discuss about the wave functions as well.